The very foundation of how our machines see the world, it's kind of built on an illusion. For decades, we've been obsessed with pushing the limits of resolution, right? We pack millions of pixels onto these tiny silicon chips, totally convinced that more clarity equals more truth. But while we were all distracted by how sharp these images look, we completely ignored a fatal flaw when it comes to the dimension of time. What we're diving into today isn't just some incremental upgrade to our current tech. No, it's what we call the synthesis of perception. It is a literal game changer in how optical hardware actually interfaces with the physical world.
In fact, the camera you're using to watch this explainer right now, it's fundamentally broken. Seriously, it's trapped in this old way of working that practically blinds it to the truest nature of motion. We trust these lenses to capture reality, but they're systematically stripping away the most vital, instantaneous moments of existence. They literally leave our most advanced machines flying blind exactly when it matters most.
So let's get into Section 1, the death of the frame, the 19th century snapshot.
Okay, let's really break this down. The core issue here is something we can call the death of the frame. See, standard video just isn't fluid. It is totally stuck in this 19th century snapshot paradigm. It relies on capturing a series of discrete, static images at totally arbitrary intervals. And those intervals, they have absolutely no relation to the continuous flow of the real world. Because it takes these rigid frames, you get this massive inflation of completely redundant data that just chokes our processors. I mean, think about it. If a camera stares at a still room, it relentlessly captures and transmits the exact same image, frame after frame after frame. It's wasting immense computational power on, well, absolutely nothing. On the flip side, we have event-based vision. This is a brilliant synthesis of biology and engineering that literally abandons the camera shutter altogether. Instead of grabbing rigid frames, every single pixel acts as its own independent autonomous computer.
Moving on to Section 2, Architecture of the Living Eye, a biological masterpiece.
To solve this massive data bottleneck with modern cameras, engineers realized they had to throw traditional optical design right out the window. If we wanted to build a better eye, we had to stop looking at cameras and start looking at Wetware, the 600-million-year-old biological blueprint that completely solved this exact problem way before silicon was even a thing. The human retina is just an absolute masterpiece of parallel processing. It effortlessly manages a staggering dynamic range of 10 billion to 1. 10 billion. But here is the absolutely crucial takeaway. Your retina doesn't send pictures to your brain, not at all. It uses a massively parallel setup where about 1 million axonal fibers send visual info using a strict all-or-none pulse code. It's like millions of tiny light switches that only flip when they absolutely have to, rather than taking a full, heavy photograph every fraction of a second. Simply put, there are no frames in human vision. Nature figured out a long time ago that recording an entire scene every few milliseconds is just a colossal waste of energy. Like, if you're staring at a blank, static wall, your retina doesn't continuously scream to your brain that the wall is still there. It only fires when something actually changes. This biological mechanism is known as the magnocellular pathway. It's this transient system that detects motion and flickers in your peripheral vision by ruthlessly ignoring redundant, static information.
Now, translating this biological elegance into actual hardware, that wasn't just some sudden breakthrough. It was a deliberate rebellion against mainstream engineering. Back in the late 1980s, Carver Mead at Caltech introduced the neuromorphic concept, basically the idea of building electronic circuits that directly mimic these biological neural architectures. Fast forward to 1992, and his student Misha Mahowald successfully developed the very first silicon retina with an asynchronous digital output. And what's really fascinating here is that while the rest of the tech industry was desperately obsessed with the megapixel race, just cramming more and more pixels into conventional cameras, these pioneers totally ignored standard conventions. They set out to build a system functioning on the logarithmic scale of life itself.
All right, Section 3, the 1 microsecond eye. Biology meets silicon. So decades of this neuromorphic research have finally culminated in a direct mechanical synthesis of biology and engineering. We've officially arrived at the creation of the 1 microsecond eye. This is a sensor that completely reimagines how a machine intercepts light. The absolute core of this revolution is the dynamic vision sensor, or DVS for short. Unlike your standard CMOS sensor that's super burdened by a global shutter, which forces every single pixel to wait around and report its status at the exact same time, each DVS pixel is a completely free agent. Every individual pixel has its very own analog circuit, continuously monitoring local illumination completely independently from the rest of the array.
So how exactly do these independent little pixels communicate? Well, they operate solely on the principle of change. When the brightness shifts by just 10%, the pixel instantly fires an event. It doesn't send a whole image. It just quickly shouts 3 pieces of info: exactly where it is, the exact microsecond it happened, and whether it got brighter or darker. And that's it. That's the whole message. By doing it this way, it creates a continuous, sparse, and asynchronous stream of data that just completely shatters previous speed limits. Let's put that into perspective. In a standard 30 frame per second camera, there is a 33 millisecond dead time between each exposure. Any movement, any change that happens within those 33 milliseconds, it's just lost, gone forever. But by ditching the frame entirely, the silicon retina hits an astounding temporal resolution of just 1 microsecond. Think about why this is absolutely crucial out in the real world. Say a self-driving car is about to collide. It no longer has to wait around for the next frame to process the danger. It perceives the threat the very microsecond the photons shift. That instantaneous reaction time, that could literally be the difference between life and death.
Which brings us to Section 4, the biological power revolution, biological efficiency. Now, this raw, unprecedented speed, it's honestly only half the story. By shifting away from this rigid, frame-based capture, we've inadvertently sparked a staggering biological power revolution. Look, traditional cameras are absolute data gluttons. They blindly transmit gigabits of redundant information every single second, and they require immense power just to process all that junk. Now, compare that to the human optic nerve. Our optic nerve transmits incredibly complex spatial data at a mere 20 megabits per second. Because silicon retinas are copying this exact biological efficiency, transmitting only the changes in a scene, they achieve up to 100 times reduction in data volume. This lets these advanced sensors run on a microscopic power budget of just a few milliwatts. We're talking about an energy efficiency that would make an insect proud.
But analyzing this incredibly sparse, asynchronous data means we have to abandon our traditional power-hungry algorithms too. We need what's called a spiking neural network, or SNN. Think of this as an artificial brain architecture that uses discrete spikes and integrate and fire neurons. To put it simply, the system just quietly builds up energy, and it only sparks into action when there is actual data to process. Instead of constantly running heavy calculations in the background, it applies true organic logic. The system computes only when an event is actually happening, perfectly mirroring the quiet, focused efficiency of our own human brains.
Next up is Section 5, Beyond the Atmosphere, Extreme Environments. The capabilities of this neuromorphic architecture are so profound that its ultimate proving ground isn't even here on Earth. We are pushing this hardware way beyond the atmosphere, right into the extreme, hostile environments of orbit, places where traditional optical hardware catastrophically fails. Up in the harsh vacuum of space, motion blur and these incredibly violent sunlight to shadow transitions will instantly blind a standard lens. But event cameras? They possess an extreme dynamic range, frequently operated between 120 to 140 decibels. This immense flexibility means a single neuromorphic sensor can peer into the pitch-black depths of a lunar crater while simultaneously capturing blinding solar glare, all without overexposing a single pixel. No way a normal camera pulls that off.
And the coolest part is the real-world applications are already active and expanding right now. Take the Falcon Neuro mission. It's operating on the International Space Station, using these exact sensors to observe rapid atmospheric lightning and these transient luminous events known as sprites. These are phenomena that flash in and out of existence in as little as 100 microseconds. Down closer to the ground in the lower atmosphere, this technology is actively tracking hypersonic flight and high-speed orbital debris. It locks onto targets moving so incredibly fast that they'd appear as nothing but an invisible blur to any conventional hardware.
Finally, let's look at Section 6, the synthesis of perception, real-time interface. So what we are observing here isn't merely a faster camera or a lighter sensor. It's really a total interface revolution, one that completely redefines the boundary between the artificial and the real. By fully ditching the artificial constraint of the frame, our machines have unlocked a level of temporal fidelity that until now was entirely reserved for the biological elite, us. We are fundamentally moving away from the era of simply recording the world as a passive observer and crossing over into the era of perceiving reality in absolute real time. We have successfully built an eye that operates in microseconds. It no longer just watches the world, it reacts to it instantly, processing photons with the precise, deliberate logic of living tissue. The synthesis is practically complete, but it leaves us facing this really remarkable frontier.
If we can create machines that can see and think with the energy efficiency of a tiny fly, have we finally reached the true limit of portable intelligence? Or are we just scratching the surface of what silicon can do now that it's finally waking up to the true speed of light? It's definitely something to think about.